change of phase due to reflections. Okay. Young's method for producing two coherent light sources involve illuminating a pair of slits with a single source. The purpose of this is to produce coherent sources, okay, for lights to interfere each other and producing fringes. Okay. Another simple yet ingenious arrangement for producing an interference pattern with a single light source is known as Lloyd's mirror. This is a setup of the Lloyd's mirror, where we have, okay, one real source symbolized as S, okay, and one mirror placed like this, and viewing screen is placed perpendicular to the mirror. Light wave from the real source S here can reach point P on the screen either directly from S to point P, represented by the red color path, or by a path involving reflections from the mirror, okay, to reach point P. So this is due to reflection. This is the path, the blue arrow here representing the path of the light wave to reach point P due to the reflections. The reflected ray can be treated as a ray originating from a virtual source S prime, seems like. Okay, so if we have extrapolation, it seems like the blue arrow here is coming from another virtual source symbolized as S prime. As a result, we can think of this arrangement, right, as a double slit sources where the distance d between the two sources S and S prime in this figure is analogous to the length d in previous figure in Young double slit experiment. Hence, at observation point far from the source where the L much bigger compared to the D, this is a condition, okay, the L must be much bigger to the D, okay. Why is it necessary? To make sure that the theta is small enough or acceptable range. We expect wave from S and S prime to form an interference pattern exactly like the one formed by two real coherent sources in Young double slit experiment. An interference pattern is observed. Okay. The position of the dark fringe and bright fringes, however, are reversed relative to the pattern created, okay, by two real coherent sources in Young double slit experiment. Such reversal, okay, how they reverse? Supposedly, in Young double slit experiment, at the center of the at point P prime here, or we call it as the center in Young double slit experiment, we supposed to observe bright fringe, or we call it central maximum. However, in this arrangement, at P prime, we are going to see dark fringe. Okay, is in reverse or opposite to the fringes produced in Young double slit experiment. Okay, so such opposition or reversal can only occur if the coherent sources S and S prime differ in phase by 180 degree. Because we have reflections happen here. Okay, so we can conclude that electromagnetic wave, which is our light wave just now, undergoes phase change of 180 degree upon reflection from medium that has higher index of refraction than the one in which wave is traveling, because in this case the wave of light is traveling from air, okay, and projected or hitting the mirror, okay, where the end of the mirror normally higher compared to the refractive index of the air, and then being reflected. So the lights that being reflected here undergoes 180 degree of phase change. That is why, okay, at this P prime, we're going to observe dark fringe. Okay, what does that mean by 180 degree of phase change? It means that, okay, if the incident lights here reaching this point astro, the one that being reflected going to be crest. We can imagine that the process of the phase change similar to the stretch string. Okay, if you recall, this is from our previous topic, right? So let's say we have a pulse meeting a fixed end. Okay, so what will happen if the incident pulse having a crest or positive pulse and it being reflected, it's going to be inverted, or from positive value amplitude it becomes negative value of amplitude, right? So goes the same for the light wave. If it is moving from lower refractive index, hitting the material with the higher refractive index is going to experience 180 degree of phase change. Okay, and this analogy is no phase change happen where the light is moving from the end is higher, okay, meeting a boundary, hitting on the material with lower refractive index. It is being reflected but with no phase change. Okay, so the same analogy goes to this. We have a stretch string where we have free end here, okay, free support here. So the pulse, the incident pulse, if let's say it is positive, being reflected back, still having positive magnitude. Right, interference in thin films. Interference effects are commonly observed in thin films, such as thin layers of oil on water or thin surface of a soap bubble as shown in this figure. Okay, the varied colors observed when white light from the sun is incident, okay, on such films results from the interference of wave reflected from the two surfaces of the films. So, let's consider this diagram representing schematic diagram for the thin film. Right, this is our film having N as the refractive index. Outside of the thin films where the ray is coming from, let's say perhaps a source or sun, okay, where here we have air with the N equivalent to 1, the film with the N is N values, and the thickness of the film is T, and then the air will be diffracted back or passing through the film and emerge into the air again. We are going to consider a film of uniform thickness T and index of refraction N. The wavelength of light, okay, lambda N in the film from section 34.4 is equivalent to lambda N equivalent to lambda over N, where the lambda is wavelength of the light in air and N is the refractive index of the film. Let's assume light rays traveling in air nearly normal to the two surfaces of the film as shown in this figure. Reflected ray 1, okay, the first ray incident upon the films, okay, and part of it being reflected. Part of it going to travel into the film being refracted. Okay, so the first ray here is moving from N lower, making the n higher, okay, material. So it's going to experience 180 degree of phase change. Right. Then another part of the ray going to be refracted and moving into the films, meeting the boundary between films and air again. And then part of it going to be reflected and part of it going to emerge, okay, into the air. Okay, the one that being reflected going to label as ray 2. For ray 2, it's moving from higher refractive index material to the lower refractive index material. So the ray 2 will experience no phase change. And of course, okay, part of it going to be reflected back and then moving out from the film into the air. So for ray 3 and ray 4, okay, leads to interference effect for light transmitted through the films, okay. And for ray 1 and ray 2, interference in light reflected from a thin film is due to a combination of ray 1 and 2 reflected from the upper and lower surface of the film. So, right, for ray 1 and 2, okay, constructive interference only happen, we see here, it has 180 degree phase change, no phase change. If we want to have a constructive interference, they both experience 180 of phase change, this one. Therefore, to make sure they are going to meet crest of this, meet crest of this, or through of this, meet through of this, to have constructive interference, somehow we need to adjust the formula. 80 degree, it means that half of wavelength, because one complete motion of a wave equivalent to one wavelength. One wavelength equivalent to 360 degree. If you want to have 180 degree, it means that lambda over 2. So to fulfill condition of constructive interference, the distance travel 2t, 2 times thickness, because this is the path different. The one, number 1, having no reflected, experiencing 180 degree phase change. Ray 2 have to travel further of 2 times of the thickness, moving into and then being reflected back. And then it can emerge into the air. And let's say we are here, we are observing here. So, the path difference taken by ray 1 and ray 2 is equivalent to 2 times of thickness of the film. So, path difference is equivalent to m plus half times lambda n. Okay, why is it must plus half for constructive? Remember, it's experiencing phase change, and this one no phase change. To make them meet crest and through meet through, we need to adjust the formula by this. Okay, so m plus half times lambda n, where the order of the m is 0, 1, 2, and so on. There is no more positive negative here. Why? Because the one that observe is our eye. Here is our eye. Okay, we have no screen on our retina, whether it exists or not. So the order going to be integer, 0, 1, 2, 3, and so on. Alright, and this is lambda n, where lambda n is equivalent to lambda over n. Right? So if we substitute this here, this is going to be no more n, it's lambda only. Right? So 2 and t, because you are substituting, you are putting this like this actually. M plus half lambda over n. Right? So 2 and t is equivalent to m plus half lambda. Okay, the order is the same. This is for constructive interference. For destructive interference, if you want to have throw mid crest, okay, if you want to have destructive or throw mid crest for ray 1 and 2 here, we don't have to change anything, right? We don't have to alter by half of wavelength here, because by nature this one having under 80 degree of phase change, this one has no phase change. By nature itself, when they combine, they are going to have crest mid throw. So the path length is equivalent to lambda m directly. But the order of the m cannot start from 0, because if you put it 0 here, that's it, nothing to be calculated, right? It's 0, everything is 0. So this is actually originate from 2t equivalent to m lambda n. And substituting lambda n is lambda over n, then you are going to have 2 and t equivalent to m lambda. Okay, this is disruptive interference. In simple, okay, basically if you have one ray having 180 degree phase change and ray 2 has no phase change, you just memorize the formula going to be, pattern of the formula going to be in opposite to the Young double slit experiment. It's just that the path difference is 2 and t instead only delta, right? So how about if we have another material placed after the films? Okay, so if you have this kind of arrangement, then the whole story of this one will be different in opposite. Okay, so let's recall just now we have this diagram, right? This diagram also known as one phase reversal. Okay, one phase reversal, right? So when you have only one phase reversal, because this one has no phase change, again for constructive interference, this is a formula. For destructive interference, this is a formula. So now let's consider two phase change reversal. So how is it happen? This is going to happen when you have a light moving from air to the first layer where we have our film here. Let's say for example silicon monoxide, okay, where N is equivalent to 1.45, which is bigger compared to N air, right? But after silicon monoxide, here you put another layer of silicon, let's say another material. If you have this kind of situation where the third, okay, material here having N highest of all, so from lower to the medium value higher of the film, N is higher, and then meeting another material where the N is highest, okay, of all. Now ray 1, we know that it's experience 180 degree of phase change. For ray 2, when the ray 1 being part of it being reflected and part of it going to refracted, okay, and then meeting a boundary between N equivalent to 1.45 to the N equivalent to 3.5. So again, it's going, part of it going to be reflected, part of it going to be refracted into the third material. So the one that being reflected, okay, symbolized as ray 2, going to experience also 180 degree of phase change, because it's moving from N equivalent to 1.45 to the higher N material, refractive index material, where the N here is 3.5. So it's going to experience 180 degree of phase change. Why there is no phase change when the ray 2, for example this case, okay, moving out, okay, after it being reflected and moving out into the air? Because it's moving from higher refractive index to the lower refractive index. So at this point there is no phase change happen, as well as due to this part there is no phase change happen, because it's moving from higher end to lower end material. Alright, for this case, it's being reflected and moving out. At this position, at this boundary, it's experiencing 180 degree of phase change because it's moving from end lower to the end higher material. Right? For ray 1 and ray 2, both of it going to experience 180 degree of phase change. That is why we call it two-phase reversal. Therefore, for constructive interference, the formula going to be 2nt equivalent to lambda m in opposite. Isn't it? In opposite. And for disruptive, 2nt equivalent to m plus half lambda in opposite. Okay, so for two-phase reversal, basically the idea is the same to the Young double slit experiment. If it is only one phase reversal, okay, so the basic idea of the formula will be in opposite. You memorize one of it only is enough. But all the time, bear in mind that your path different now is 2nt. Because the ray need to travel 2 times of the thickness for our films. Alright, so the effect of this, one of the effect is about the colors of things in nature that Allah created so nice. Color is changing from one perspective or one angle to another angle when we observe the bird. This effect we call it iridescent. Example 36.4, non-reflective coatings for solar cells. Solar cells, devices that generate electricity when exposed to sunlight, are often coated with a transparent thin film of silicon monoxide, or N equivalent to 1.45, to minimize reflective losses from the surface. Okay, minimize, the keyword here, minimize, okay, reflective losses. Right then. Suppose a silicon solar cell, N equivalent to 3.5, is coated with a thin film of silicon monoxide for this purpose. Determine the minimum film thickness. Again, another keyword here, minimum film thickness. Right? That produce the least reflection. The least reflection. This is another keyword. Okay, at a wavelength of 550 nanometer near the center of the visible spectrum. So order of the film going to be minimum, going to be 0, or it also could be 1. But if you see the diagram here, both ray 1 and ray 2 experiencing phase change. Therefore, the formula for constructive or destructive going to apply for two-phase reversal formula. So, least reflection, it means that disruptive, because we cannot observe disruptive interference. We don't want to observe. We don't want it to be observed. So that's the idea. So we want to have disruptive interference. So the formula for two-phase reversal is going to be 2nt equivalent to m plus half times lambda. And we know that the order must be minimum. So m equivalent to 0, because the least thickness, the minimum the order is. So if you substitute m equivalent to 0, you will get 0 plus half times lambda. So here, formula going to be 2nt equivalent to lambda over 2. That is how we have this formula actually. Right, so rearrange this formula, you will get t equivalent to lambda over 4n. Then now you may substitute the rest of the information of the lambda and the n. So the n here, which one? Is it 1.45 or is it 12.5 just now? The one that had become phlegm. Okay, so our phlegm is silicon monoxide. So you're going to substitute 1.45. Alright, so you will get the thickness is 94.8 nanometer. That's all for this topic. Thank you for watching. Do not hesitate to ask any question regarding this lecture. That's all. Assalamualaikum.